Welcome back. So I left you with this, which is the simpler notation for functional dependencies. AB functionally implies DE. Maybe something else for your intuition. One way, especially, we're going to have hundreds of these in the coming slides of these functional dependencies. We look at the axiomatic aspects of this. One way you can think of it, and that actually helps me with the axioms to understand the derivations, is that when you have this, it basically means, imagine we play a game. I have a record that I picked randomly in the table. I don't tell you which one. And I only tell you the value of A and the value of B for that record. And then I ask you what you think the value for D and E is. Well, if you have a functional dependency, AB functionally implies DE, it means that if I give you A and B, you will be able to give me D and E just by looking at the table without knowing which tuple I have. So you can think of it in these games. Like if I know the value of A and B, then I also know the value of D and E, right? And you can think of real life examples. For example, imagine that I pick a student at random and I tell you their Leggy number. Well, maybe you don't have access to the database of ETH, but let's say I have a sysadmin at ETH and I give, okay, this is the Leggy number. Do I know the first and last name? The answer is yes. If you have the Leggy number, then you know the first and last name. So you would have the dependency, Leggy number functionally implies first name, last name, and so on. The same goes for a course unit number, right? Every lecture at ETH has a number. If I give you the course unit number of this lecture, then you know the name of the lecture, you know who's teaching, and so on, right? So there's plenty of examples like this. So you can think of it again as, if I know A and B, then I also know D and E, having access to the table, of course. All right. So that way, you see the difference between before. Here I had this set and these quotes and so on, and now I'm just being lazy and I use this simplification. I just write products functionally implies price. Okay. Now you see, if I keep using that notation, that price functionally implies customers does not hold. The nice thing is that in order to prove that a functional dependency is broken, it's easy. You just need one counterexample. Right? It's kind of mathematics. If you need to prove in math that for every function, this and this is true, might be complex. But if you want to prove that it's not true, all you need to do is show one function for which it's not true. So since the definition of the functional dependency says for any two tuples, if they agree on S, they agree on T, all I need to do to prove that it's not true is just two tuples. And if they agree on S and don't agree on T, that's it. I've already proven that S functionally implies T is not true. So all I need to do is find two tuples that agree on price and that disagree on customer. And this is exactly what we have here. I found two tuples. They agree on the price, but they disagree on the customer. That's enough. That's all I need to say that this doesn't hold for the table. I just need one counterexample. The other opposite direction, of course, to prove that it does hold, then you really need to check everywhere that it's always true for any two pairs of tuples. Or you can use the axioms, as we will soon see. All right. Now it's just to play around. I'm giving you an alternate definition. Technically, mathematicians call it a characterization. It's not the definition, but it's a criterion that allows you to characterize a functional dependency. So I'm going to have a visual for that. Technically, you can characterize that S functionally implies T if when you pick any tuple, I'm calling it F, you pick any tuple in the table, and then given that tuple, you perform a selection on the table, and you look for all the tuples in the table that match with F on the values in S, right? So you select all the tuples that have the same value as there is in F, and then you project on T. If you get a singleton, always for any F, then that's a functional dependency. But it's better with an example here. So let's say I want to use this characterization here with this table, and I want to see if products functionally implies price. Here it's true. You can see visually that phone is always 800, laptop is always 2000, and so on. So it's true. But let's see now our characterization. I'm picking one one small tuple f. All I need is the product. I don't care about the rest. So I'm picking one value for the phone. In that case, I could have taken the laptop. I could have taken the TV. And now look at what I do. I'm having a selection, sigma. The product must be this phone in F. So now I project on all the products that are phones, right? This is a selection because it selects rows. And then I project on T. What is T? It's the price. So of course, here I just lazily deleted the columns, but you remember it set semantics, so the duplicates should go away. What do I get? A singleton. If I do that, the projection on the price of all the tuples that are phones, I only get one single value. If you do the same here with laptop, you're going to get a singleton value of 2000. If you do it on HGTV, it's a singleton value of 1000, right? So selection on an arbitrary value followed by a projection on T gives you a single value. For whom is that clear? For whom is that intuitive? Not quite, okay. So you would handle it precisely by normalizing in the way, meaning that you would have a table of products with the current price, let's say. Then you would have another table that have the orders of the customers with the 9 items, and then you could store the past prices. And the reason you could do that is that you spread over multiple tables, right? And the fact that you see this problem, that this is very restrictive, is because this is bad design. This whole thing is bad design. This is what you should not be doing. And what we are trying to characterize is formally why this is bad design. That's what we are trying to capture. So you're making an excellent point that this doesn't capture real life. And one of the reasons is what you say, is that the prices can evolve, people can place different orders and so on. But whoever designed that schema probably had in mind that they wanted to capture the current price and so on. But again, it has the drawback that you mentioned, right? So that is a very good point, right? In general, actually, we will see, that's the intuition that you'll develop this and next week, is that most functional dependencies will want to avoid. This is something we try to avoid. If you have too many functional dependencies in a table, that's usually a sign that the design is bad and that you should split the table into multiple tables, right? All right, but since I need to build the functional dependencies, I have to take these bad examples to show why these are bad examples and show the functional dependencies in there. All right, so this works. All right, and yet another way with natural words to characterize a functional dependency is that technically it's as if you had a function, a mathematical function from S to T. Right, so for example, here we could see this dependency from product to price as the existence of a function that associates every product with a price. And that function should be easy to see, right? That's the function. Phone is mapped to 800, laptop is mapped to 2000, HGTV is mapped to 1000, right? And because we have a function and we can express the price as P of product, where P is my function, that's the one below, then this is a functional dependency. So now you probably understand why it's called functional dependency. It's because of this. It's because we technically have a function from the values in S to the values in T. For whom is that clear? Right? So I gave you maybe 4 or 5 different intuitions behind this, that they're all equivalent, but these are all ways of looking at the functional dependencies. All right. So that was my next step. What have we done so far? I told you about the update, delete, and insert anomalies. I gave you the intuition of bad design and the fact that you should really have multiple tables that each do one thing rather than a big table that does too many things. Then we introduced the concept of a functional dependency that puts a constraint on a table. And we defined it in multiple ways. And now I'm moving on to the next part, which is called super key. So it almost sounds like something you would have in a TV show with such a cool name. Anyway, what is a super key? I'm dropping, as always, the formal definition, but you will see this one is actually not so scary. So a super key is a set of attributes like S or T we did before. Now I'm calling it K because that's going to be a super key, right? But I could have called it S or T. K is a super key if we have the functional dependency. K functionally implies everything, all attributes in R. So let's say R has all letters from A to Z, right? Then we have, if we have the functional dependency, K functionally implies A, B, C, D, blah, 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 Y, X, X, Y, Z, then K is a super key. I basically managed to find some attributes. If I know them, I know the whole table. I know the whole records. I know all the values in the records. Right. So this is called a super key. If I express it differently, but you will see it's just another way of looking at it, it means that if I take any two tuples, T and U, if T and U agree on K, then T and U are the same. The only way two tuples can agree on all values for the attributes in a super key is if they are the one and same tuple, right? So you can check if two tuples are the same just by checking on K, on the super key. All right, so let's take a look at as an example to try to make ourselves familiar with super keys. So this is a table, it's different, it's a different table than what I showed you before. We have a product, phone, laptop, TV, we have a price, we have a category, high-tech for phone and laptop, entertainment for the TVs, high-tech for a headset and so on. And then we have stock. So now it's an inventory table, right? It's what I have in my warehouse. All right. Now, this is a super key. Phone, laptop, HDTV, 4K TV, headset. How do I know? Well, it's because I have the functional dependency. Product functionally implies product, price, category, stock. If I give you the product, then you know the price, the category, and the stock. Let me show you how that works. Let's say I'm saying, okay, product is HDTV. What is the stock? 2. You see, you know the stock without me giving you further information. If I tell you the product is laptop, what's the category? High tech. And I can do it with any one of the columns. If I tell you the product and I ask you for the value of any column, you will be able to answer me. This is a super key. All I need to know is the product, and I know exactly what record this is, right? So to give you an intuition, for example, if you have a table of students at ETH, the login number is a super key. If I give you the login number, you know what student this is. If I give you in a table of courses the course units, then you know what course it is. All right. Yes? You're making a very good remark. So I'm repeating on Zoom for the people to hear. So it's basically on the difference between a super key and a primary key. A super key is part of the way we define the primary keys, because in fact, the primary keys will be derived from this. I'm going to show you a counterexample now of something that is a super key, but it's not a primary key. This here is also a super key. How do we see it? Well, let me tell you, product is headset and price is 300. What's the stock? 4. I could do it for any columns and any values for product and price. So it's a super key, right? This is a super key also, right? So you see that a super key is basically more general than a primary key, right? Because technically, if I have a super key, if I add attributes, it's still a super key, right? So in a way, and we'll come to that, the notion of primary key contains the notion of a super key, but it also has the notion that it must be minimal. It has to be as little as possible in there. And I'll come back to that. Does it answer your question? Yeah, awesome. We have another question. You need the table to answer that question. Yeah, so when I use the word know or know the value, it's in the context of my thought experiment with the game. So it goes like this, again, it's exactly, yeah, at least it contains an ID. It could be more because this is also a super key, right? But the notion is really this. I give you this table here, and I'm secretly picking one of the records without telling you what record that is. And then I'm telling you my record has, as a product, laptop. So now you know that my record has the value laptop. And I'm asking you, do you know the price? And you're going to tell me, yes, you know the price, it's 2,000. And if you can answer, if you know the product, if I give you the product, then you can tell me, I know the price, I know the category, I know the stock, and it works for any record that I might have secretly picked, then this is a super key. Yes, this is you basically just came up with a characterization of a super key. One of the characterizations of a super key is that it only has unique tuple values, right? So we can see that here it's a super key, this single attribute, because it's all unique values. And you're absolutely correct. If I have a column and all values are unique, then that column is a super key. Exactly. Yeah, it's not a super key because let's play the game. I'm picking a tuple at random, secretly, and I'm telling you category is entertainment. What is the product? You don't know. Maybe it's HGTV, maybe it's 4K TV, but you don't know. You don't have enough information. You see? So in that case, we don't have the functional dependency category determines product, because if I say entertainment, you don't know what the product is. And thus, category is not a super key, because it would need to functionally imply everything to be a super key. Does it help? Yeah, go ahead. Mm-hmm. Yeah. Mm-hmm. Then it cannot be a super key. So yeah, go ahead. Mm-hmm. Mm-hmm. Exactly. You cannot have duplicates, right, because of the set semantics. In that case, I'm using the set semantics here. Yeah, but if you're correct, if I was using the back semantics and I would allow duplicates, then indeed that definition would no longer be correct, right? I would have to say t dot all the attributes equal t u dot all the attributes, but I would no longer be able to say that t equals u, right? Yeah. So you're absolutely correct. But I'm really assuming set semantics for the entire lecture that we are doing now. Yeah, so this is why it's mathematically consistent. Yeah. Okay. Any other questions? Very good. All right. So this is the super key. This is the super key. This is a super key. This is not a super key. How do I know it's not a super key? It's not unique. Exactly. That's how you tell. 800, 800. So if I pick a tuple at random and I tell you the price is 800, then you don't know the product, right? So that's not a super key. That's also not a super key. That's also not a super key, and so on, right? So you basically have the intuition. And indeed, the super key, from an intuition perspective, it does have to do with, is everything unique? Are all the compound values across these attributes unique in my table? Now, a few simple theorems that you can play with, just in order to make sure you understand the framework. It's almost trivial theorems, but you can think about this. First, the set of all attributes of R is always a super key of R. For whom is that clear? Okay, it's because we have a functional dependency that is trivial, right? It's always true that S functionally determines S. If I tell you that it's a phone and then ask you what is it, and you tell me it's a phone, right? That's trivial. Second, so that's really for the purists in mathematicians, if R is empty, then any subset of the attributes is a super key, right? But that just has to do with the fact that we have a for all here. We have a for all, but a for all T and U in an empty set, that's always true, right? So this is the reason. the reason here. Then let me look at a table with only one record, one row. Then any subset of the attributes of R is a superkey of R. For whom is that clear? Right. And here, even the empty set is a superkey. It's easy because if it's only one record and I ask you for the value, you can tell me the value, there's only one record. All you need to do is tell me the one value that there is in the column I'm asking for, right? So this is why. Then let's look at the table theorem 4. One attribute, two records. So we have one column and two rows. Then the set of all attributes of R is the only superkey of R, right? So it means that, so it's obviously a superkey. The set of all attributes is always a superkey, that's theorem 1, but it's the only one. So what I'm telling you is that it has one attribute. What would be the other set of attributes? That would be the empty set, right? But since we have two records, the empty set is not enough to know which record it is. And then theorem 5, if R has two records and any number of attributes, then the superkeys of R are exactly the subset of attributes that include at least one attribute on which the tuples differ. This has to do with the fact that the superkey must be discriminating. It must give you enough differentiation between the tuples to tell. If the superkey doesn't differ across the tuples, then you cannot differentiate between the tuples. Okay? Does it make sense? You can think of it offline, but it's just, you know, the sort of things that you can actually start proving mathematically. So you see, it's a whole framework that we spend even more time with the computer scientists in the bachelor's level database lectures. Okay. All clear? Who is following? Okay, I'm really going step by step, trying to give you the intuition because that's a lot. That's really a lot to digest. So far, when I told you about functional dependency, or when I told you about a superkey, I was always talking about a table. I gave you a table and I asked you for that table, does that functional dependency hold? Is that a superkey and so on? What about universes of tables? Because again, in real life, you have a website and the tables have a life, right? So what about a universe of tables? So now I have a set of tables that are my universe, and I'm asking about the definition of functional dependency and superkey. When does it hold for my entire universe? It's actually quite easy. It basically holds for the universe if it holds for every table in the universe. It's that simple. So basically, given two subsets S and T of the attributes of my schema, so the one that all tables in my universe have in common, then I'm saying that S functionally implies T for you if it's true for any table in U, right? And S is a superkey of U if S is a superkey of every table in U. That's what it does, right? Why am I telling you that? Because there is a bit of a tricky thing that sometimes can cause a bit of confusion, and I want to take a bit of time to explain that to you. Look at this table. I changed it a little bit. Is that a superkey stock? In that very table here, yes, you can tell because the values are unique. 10, 3, 2, 9, 4. If I tell you the stock is 9 and I ask you for the product, you can tell me it's 4 KTV, right? So it's a superkey. Yes? Yeah, exactly. That's exactly the thing. It is by accident right here. It's by accident. We were just lucky that at that very point in time, it turns out that the values are different. But if you wait a little bit and let customers order things, like imagine that somebody is ordering a laptop, then that goes down to 2, and now it's no longer a superkey. So this is the reason why it's what I wrote here. It's a superkey, but it's not by intent. It's not by design. It's really just an accident here. And so here's more generally what happens. You have the universe of all the tables. That's your inventory, and you have maybe billions of possible tables that can happen across time. For Amazon, it's surely billions. So stock is definitely not a superkey, right? In general, if I take some inventory and tell you 3, and I ask you what products are such that there's 3 of them, you cannot generally tell me, right? That wouldn't make any sense. So technically, stock is not a superkey, right? Because most of the time, it's not going to superkey of the table at a point in time. However, once in a while, just by luck, it will so happen that it's sometimes a super key. So in that case, the first and third tables are the typical tables. It has to do with typicality, if we have physicists here. And in the middle, I have something atypical. It's not a typical table, it's just an accident. We happen to have now a super key. What you need to be careful about here is that the table in the middle, I would say, is not representative of the universe. It's not a typical table of the universe. The first one and the third one are typical tables. The one in the middle is not a typical table. Now, how do we handle it, especially for the exam? Because that can cause confusion. What we try to do in the quiz and in exams is when we ask questions about super keys and candidate keys and what I'll explain later, we try to always give you typical tables, representative tables. So we might give you the first one or the third one and then ask you for the super keys. We will avoid giving you a table like the one in the middle, because this one is not typical, and that just creates confusion because you have a super key that shouldn't be generally a super key. So this is why I have this little word of warning between the notion of a universe of tables and the notion of a table, that you have attributes that are generally not super key, but by accident, at some points in time, they become super keys, right? Now, in that case, it's because it's a small table with 5 items, but if you take the entire Digitech or Amazon inventory, I think it's extremely unlikely that you're going to have any moment in time where all the inventories are unique. Extremely unlikely. So as a big web shop, that really doesn't happen. If you want, just for what I mean with typicality and typical, if we have people interested in physics, it's really a bit like saying that, you know, right now I'm looking at the position of the molecules in this room. They're spread throughout the room, right? We don't know the exact location of every molecule, but we still sense some sort of temperature, pressure, and so on, right? This is what we can feel. Now, you could imagine, because that's a possibility, that suddenly all of the molecules in the room are here, and there's nothing left here. It's a possibility, but it's so atypical that it's just not going to happen. The probability that it would happen is so small that for all practical purposes, that's not the case. So a typical way that the molecules are in this room is filling the entire room. Having all the molecules in a portion of the room would be not typical. So this is just another way of looking at this, all right? So it's not representative. For whom is that clear, right? That this can happen by accident and so on. All right. So again, for the exam, we try to be careful with this. And we even usually write a small comment, like you can safely assume that the table we're giving you is representative and typical of the universe that we consider. Okay. Who's ready to move on? Clear? Super keys? Functional dependencies? Okay, so let's move on to candidate keys, which brings us closer to primary keys. So what is a candidate key? A candidate key is a minimal super key. But I need to be very precise on minimal because this is the source of confusion every year, what is meant with minimal. So you see the definition here. That's the part right there, checking the time as well. Minimal here means that if you try to remove an attribute, it's no longer a super key. That's what minimal means in terms of sets, not in terms of the number. The common confusion is that minimal is interpreted as the number of attributes in U. It has a minimal number of attributes, but that's not about this. It's not about minimal. It's really about every attribute in K is necessary. You cannot remove anything without it no longer being a super key. That's minimal. So here's an example here. AB is a super key. Who agrees that AB is a super key for that table? It's a typical table, again, doesn't have accidents, right? AB is a super key. You can see because if you know A and B, then you know C. For example, if I tell you the value of A and B is small a, small c, what is C? 2, right? It's the second record. So AB is a super key. BC is also a super key. AC is also a super key. And ABC is also a super key, right? If I add attributes, it's still a super key. What you can see here, however, is that ABC is not minimal. Because when I have ABC, I could remove A, and that's a super key. BC is a super key. I could also remove B or C, right? But basically, it's not minimal. So the candidate keys are AB, BC, and AC, but not ABC. It's all the keys such that I cannot remove any attributes, right? But again, it doesn't have to do with the fact that they contain two attributes. It has to do with the fact that there is no strict subset that would be a super key. That's what it's about. Here, for example, this is a super key, right? We saw they're all unique. This is also a super key. This is also a super key. This is also a super key. But these three here, this, are not minimal. Why? Because I can remove. So now I cannot remove anything anymore. So this is a candidate key. This is not a candidate key. It's not a candidate key. It's not a candidate key, right? This is not a super key. This is not a super key. This is not a super key. So we don't care. Not a super key, not a super key, not a super key. So here I try to have all of them. And the empty set is also not a super key. All right. This is a candidate key because I cannot remove anything in there. If I remove, the only thing I could remove is product, right? But if I don't have any information, since there's more than one record, then you cannot tell which one it is. So it's a candidate key. And here, it's an example of a super key that is not a candidate key because you could remove the price here and it's still a super key, right? So none of the strict subsets is a super key. So you might have noticed that when I give you the definition here, I was a bit careful. Where is it? Here. I give you the definition of a candidate key on a universe of tables. I didn't give you the definition on a specific table, but on a universe of tables. Why? Because again, it has to do with the fact that we try to figure out a primary key when we do that. And when you try to figure out a primary key, this is something that you do with the schema of your table. So it's really your intent in the design. You don't look at a specific table. You look generally at all the potential tables. So I was very careful in there. However, I could also extend the notion of a candidate key to a single table. But again, word of warning, do not do it unless the table is typical or representative. If you do it on a table, like if I go back here, on a table like the one in the middle, and you start talking about candidate keys, this just doesn't make any sense because you have these accidental super keys. So what's going to happen is that suddenly stock here is also a candidate key. Right? And a candidate key, again, is something that you would potentially make a primary key. Does it make any sense to say that stock is a primary key? No, in the intent of the database, it doesn't make any sense. The reason is that it's not representative, what we are looking at here. Generally, stock is not a super key. So this is why it might be that we ask for candidate keys at the exam, but when we do that, it's always on a representative table. You can safely assume that the super keys here, they match generally the ones in the universe. So you would not have weird candidate keys, all right? So really, I just wanted to make sure that word of warning. Basically, and you can actually try this to think about it as an exercise. Yes, go ahead.
Or priorities add because that like isn't it the same in the end, like isn't it like okay, strictly the kind of keys like kind of things you minimize your amount of column, not the primary key, what's up different. Like, I kind of forgot what the primary key and the rest.
Yeah. So let me then tell you about primary keys then, based on that. Basically, there's a reason why a candidate key is called a candidate key. It's called a candidate key because these are candidates to be primary keys. So basically what happens is that you look at a representative table or your schema, and you look for the candidate keys. It means that AB could be a primary key, BC could be a primary key, AC could be a primary key. What that means is that now, as the designer of the table, you have a choice. It's your choice. You can decide, and this is your decision, like I herewith decide that my primary key is AB. Or I could decide instead, no, BC is my primary key. So the relationship between primary key and candidate key is that the primary key is one of the candidate keys. Which one? It's your decision. It's whatever makes sense. Could be any of them. But it is singled out. The notion of a primary key, there is only one primary key chosen by you among the candidate keys. Does it make sense? So a primary key, because it is a candidate key, will always be minimal, a minimal super key, but it has this idea that you pick one of these as the primary key. Yeah? Yes, go ahead. Super keys is given by, it's basically the functional dependencies. You basically look at your attributes, determine all of the functional dependencies. Based on these, that gives you the super keys. You basically look for all of the functional dependencies where you have something that functionally implies all of the attributes. And then that's a super key, right? It's all depending on the functional dependencies that you have, okay? So the only one that's arbitrary is the primary key. The primary key is an arbitrary choice of you by design. But all the rest, super key, candidate key, is all mathematically strictly defined based on the functional dependencies that hold and do not hold, right? All good? More questions? No? Okay. All right. Super key, candidate key. And again, that's the difference between super key and candidate key. Super key doesn't need to be minimal. And I have a few theorems for you. The first theorem that you can think about is that if I give you a relational table, and again, I assume it's typical and representative of the universe, then there's always at least one candidate key. It cannot be that you don't have any candidate key, cannot be zero, right? And that has to do with the fact that it's something that is minimal in a finite set, so it always exists. Then theorem 2 says, it's really about these corner cases. If the table is empty, then the only candidate key is the empty set, right? It's just because the empty set is a super key always, if the table is empty, and you cannot remove anything from the empty set, right? So it's the empty set. If it has exactly one row, then the only candidate key is also the empty set, because if we play that game and I ask you for the values of the record, but there's only one, then I don't need to give you information for you to know what the record is. There's only one. And then theorem 4 says if a relational table has exactly one attribute and two rows, then the set of all attributes of R is the only candidate key. Well, all attributes means the one attribute. What it means is the empty set is not a candidate key. All right, you can think about it offline just to convince yourself. It's a good way of, exercising a little bit with all of these definitions. And now, and this is coming back to your question, we, the designer, arbitrarily pick one of the candidate keys and promote it as the primary key, right? It's your choice, whatever makes sense, okay? For example, here, in that case, based on that table, it's actually not typical because people could have the first and last same names, right? They could have the same. In that case, it turns out that they're all different. But if you don't know that, you might be wondering, okay, should I pick customer ID or first name and last name? But of course, you probably guess that customer ID is a better choice for the primary key. And again, the reason is that first name and last name, that would be an accident. It would be just by chance that here we have all distinct values. In real life, that's not going to happen. We might have several people with the same names, right? So this is why we pick here customer ID as the primary key in here, right? For whom does that make sense? Yes. At ETH, it would be your leggy number. For the tax office, it would be your social security number and so on. Okay. Now in practice, the way we write it, you find it in some textbooks, is that you write the sequence of attributes like this, the super keys, the candidate keys, if you really want the curly braces. And what's going to happen very commonly is that when you write down the schema of R, typically you list the attributes of R in this way, and you underline the primary key. That's what you typically do. Note that the primary key might have multiple columns, right? Then you underline all of those that are in the primary key. In that case, I underline customer ID, and then first name, last name. I might also add the types in there, right? That I can also do, but basically this is it. So if you ever see something like this, a list of attributes and some are underlined, then it means that these were chosen as the primary key. Yes? That's a great question. That's exactly, so it gives me an opportunity to again comment on that. The notion of minimal superkey is not about the number of attributes. It's about minimal with respect to inclusion in sets. So it means that if you just look at the size, you might think, okay, minimal is 1 because it has only 1, and first name, last name is not minimal because it's 2 and that's greater than 1. But this is not what it's about. It's about set inclusion. The reason why first name and last name is also minimal is that if you remove first name, last name is not a superkey. If you remove last name, first name is not a superkey. That's the reason why it's not minimal. So you might have several minimal superkeys, but they might have different numbers of attributes, and that's fine. Right? It really has to do with the fact that we have this notion of inclusion between sets, and the notion of inclusions between sets, basically, it's not like comparing different numbers, right? So the idea is that if you have numbers, like if I tell you A and B, either A is going to be less than B or B is going to be less than A, or they're the same, right? But with sets, it's not like that. If I give you two sets of attributes, S and T, maybe S is included in T, maybe T is included in S, maybe both, S equals T, but there's a third possibility. It might be that neither S is included in T, nor is T included in S, right? There might be like a Venn diagram. That's the reason why we got that sort of things in there, right? So I'm really glad you asked the question because it's every year a source of confusion. So it gives me the opportunity to really make it clear. It's not about the number of attributes. When we say minimal, it's about the inclusion, set inclusion. There is no strict superset of a candidate key that would still be a super key. In that case, first name alone or last name alone. For whom is that clear? Okay, question over there. Not necessarily. Not necessarily. It's really arbitrary. It's your choice. It's really a real world decision here. I'm looking at this. It's a real world decision in the sense that since I know that in the real world, first and last, is not enough to characterize a person, it's much safer to take customer ID as primary. It could be, but maybe you have several competing candidate keys that all have the same number of attributes, right? So it doesn't always tell you, right? So you could basically automate by saying, okay, I try to optimize by picking the smallest possible one, but it's really in the end a real world decision. It's really about thinking about the real world and what is it that really characterizes a record in my table, right? Okay, yes, questions, go ahead. Yes, but again, this would be accidental. It would be just because I happen to have, here I was careful to put ADA to basically make it clear, and Euler, but it would be an accident. And that's why I have my word of warning here. Exactly, it's an accident. I picked that example on purpose to basically warn you about that. In that case, even the first and last is an accident in that case. Yeah, go ahead. Mm-hmm. Yeah, let me explain. Just checking the time. So, oh yeah, so very quickly, and we'll finish on that. Where is my example? Here. The idea is simple. Try to remove attributes in here. Let me remove that. Is first name a super key? No, it's nowhere here. Is last name a super key? No, it's nowhere. This is why it's minimal. You cannot remove anything. That's what it means. Ah, yes, but then you can also remove first name and you end up with customer ID. This is also not a candidate. Oh, it's minimum because here you cannot remove any of them. If you remove this, it's no longer a super key. If you remove this, it's no longer a super key. Yeah. Yeah. All right. Do you want me to answer one more question? Okay, let me do that. Yeah, go ahead. On the table right here. Yeah. Yeah, exactly. Yeah, exactly. And again, yes, exactly. No, that's with the tuples. But typically, when you do it in practice, you might not have the tuples, and you're going to do that based on thinking. You're basically just going, okay, is it the case that this? And you're going to reason with the functional dependencies, right? But I just wanted to give you a basis. It's like an axiomatic basis for this. Exactly. Exactly. So it's really, most of the time when you design the schema, you might have dummy tables where you put some fake data just for the purpose of thinking, but it's really a high-level thinking about the real world. Is it the case that a customer ID characterizes a customer? Yes, and so on, right? Okay, does it answer your question? Awesome. So we are going to continue the whole next week. We are going to continue to think about that. So try to digest this. You can read the textbook also. There's plenty of information in the textbook. I give you the chapters. If you have questions, I answer them next week. And we'll take all the time we need because, again, this is very complex. It's a lot to digest. And we'll just take the time to go through this. So thank you very much, everybody. Thank you for asking so many questions. That's exactly as it should be. And enjoy the exercises. We designed with the TA team a beautiful exercise with candlelight charts for stock market data. And then that's a graded quiz that you can solve with writing SQL in the Jupyter notebook. Thank you very much. Have a great weekend and see you next week.